So, can you see my screen, Sensei?
Yeah.
Okay. So I rerun the analysis for the. I tried the viscous wall from the properties, and I convert to for the coupling beams, and this is the interstory drift. This is the graph I plot based on how many layers that we propose inside the damper by using this formula, and C and K we get from the viscous wall properties, and this is the
Do you remember how much uh, damping force in case of
400 sensei for each beam.
no hysteresis damper we used before?
400 maximum.
400 maximum. Could you go back one slide?
This one? This
No,
one?
no, no. Next one. So 400. So viscous damper damping force exceed 400
Mm,
in case of high velocity, right?
yes.
And in case of 30, maybe the centimeter per second is a unit.
Yes.
So in this case, 600. So how to say that? So this is a coupling beam,
Mm-hmm.
right? And in the center, we have a damper. And we designed this damper,
Mm-hmm.
and this part is steel beam, right?
Yes, sensei.
So we want to avoid yielding of steel beam.
Mm.
We design damper to, yield, fast. So if this yielding, and this steel beam is okay, no damage,
Mm-hmm.
right?
Yes.
But in this viscous damper, this damping force is very high.
Mm-hmm.
So I think in some case I observed yielding at the steel beam.
Mm-hmm. Yes, sensei. Um, and I have a few things to show you. I found this book, reference book, sensei, by Christophilus. Do you remember last time I showed some paper regarding Christophilus?
Yeah.
So he actually have this book reference. He have everything about damper. For chapter 6, he discuss about coupling. Viscous damper and viscoelastic damper. So basically here,
Okay.
he explained about how to consider hysteresis behavior in viscoelastic, and he also discuss about viscous damper. So, and yesterday I realized something. When we use viscous damper, the configuration is different. So it's in series spring, but
Yeah.
if we use viscoelastic, it's a parallel series. It use a Kelvin solid model. So I wonder if it would make different with the analysis result.
Yeah, it's different, of course.
So is it okay if we, because this one from Sierra we using a series model, but in actual reference, like from, for example, from this study, they use a Kelvin model which is in parallel, and I also check others research paper that using viscoelastic. Actually they are using rather than series.
But
So
how to decide
the
this
properties.
spring? Yeah.
So in this book, sensei. So in this book, they he also give a properties. So basically, the properties of the viscoelastic based on K and C, and G E and G C. So here he gives some value. There's three type of material A, B, C, and different temperature. And from here, he gave GE and GC at circular frequency. And here is the size and the thickness that he given. So we have shear area. and have thickness. And this is the hysteresis. So basically, we can see that these three different have different properties, and we can see the shape of hysteresis also different. And here I calculate the C. I take 24 degrees, around 24 degrees Celsius. So here we can compare the K and C. So for model A, which is have more elongated shape for the hysteresis, it have a higher C and lower K. But if we see model K, the hysteresis, the stiffness is higher compared to the damping factor. So here also we can see the K is higher compared to C, while others C is higher compared to C. And here is, but when I run the analysis, the result is not much difference. So yeah,
How did you run
run
model
uh,
ABC?
time history analysis. I use artificial acentro and Kobe,
And
and
you applied viscoelastic material?
yes, I put inside if I open Stera.
No.
Okay. For example, this model C. So I put in these properties in C.
Yeah, but the stiffness is not the same as in the book. This is a, this is we call point type.
All
So
top.
spring
Yes.
is connected in series.
Yes. So
But you are, how to say, you want to do stiffness spring with parallel
yes, in C. But
number.
I cannot use this type of viscous temper. I think.
Uh, Actually, this model represents something like this. Suppose you have a, let's see.
Mhm.
So,
Should I stop sharing, Sensei?
no, no, it's okay. It's
Okay.
okay. Suppose you have a frame
Mm-hmm.
and the damper is breast type.
Mm-hmm.
Okay, and this is C
Mm-hmm.
and this is K.
Yes.
Okay? So in this case, whole damper
Mm-hmm.
is K and damper dashboard is
Mm.
in parallel.
Yes, Sensei.
Okay? So this is a, so this model represents some kind of a connection, stiffness of the connection,
Mm-hmm.
the damper. So if you increase this value, it doesn't affect so much.
Mm-hmm.
So yeah, it's almost rigid, too much
Okay.
stiff.
Yes.
But if you make it in parallel,
Mm-hmm.
like this,
Yes.
and if you make this stiffness very large, damper doesn't move at all.
I see.
You know? So, and I don't know
S-
if it's necessary to apply this
mm.
one.
So the most important is the value of C, Sensei.
Of course, of course, of course.
Mm. I also try another model here based on this research paper. Also, guidance by quadruples. The value is much more smaller compared to the one that he gave in the books. So the result is the shape of the deflection is not much, and it's not much difference, but it have more drift compared to the first one. Yeah. So
So you input this property in Stirrup.
yes, Sensei.
Oh.
This is much
How about
smaller.
this value? Is this value is similar to oilless material?
Uh, Oilless is this one, Sensei. I calculate here. C and K. Not
50,
much difference.
51, 100, 150.
Yes.
Okay, and could you show me again?
This one.
This is
See. The lowest amplitude is 30. and working strain is 26, and the highest strain is 26. I think the stiffness is more different, not much.
And what is the damper you tried? 14.
This
Slide
one,
14.
sensei.
Yeah,
It have elastic damper, and
yeah.
at the end it have stiffener.
Yeah. I think this is a good idea because this damper is very strong. So in your case, it is exceeding almost 600 kilonewton. Right? So if you have a very weak hysteresis damper here, suppose this is 500 building, and if you put it in series, the damper force doesn't exceed 500 because if 500 shear force happens, this hysteresis part will start building, and the shear force doesn't increase anymore.
Yes.
Right? So the middle part is also doesn't increase. So it is a good idea to put the hysteresis damper in series.
Sensei, I have one idea. What if the stiffener, can we change it into the Adder's damper? Like we combine elastic with Adder's damper. Is it possible?
I was thinking also this same idea. Yeah. Okay. Maybe. So in this case, how can we make a model of Stira?
It should be connected as a series and parallel. I think we use viscous the same as this ones. Like the hysteresis for metallic damper should be in K, and the elastic should be C.
Could you click OK?
Okay.
Could you click OK? And okay. So you want to use both damper in one beam.
Usually, previous research, they always use like kind of stiffener in between the elastic, viscous elastic, but I never see people use either damper or metallic damper to combine with viscoelastic damper.
Yeah, well, easy way is you connect three beam like Stella, and this one has a Adams damper here.
Yes.
And the middle one is a
Viscoelastic
damper. And the right one is Adams damper again.
Okay.
But you must be careful the length of the beam.
Yes, sensei.
I don't know.
I will check how to arrange them.
Well, if you make it small distance, you put another steel.
Oh.
Just the elastic steel. So that, for example, this is 50 centimeter. 50 centimeter. 50 centimeter. So in total 150. But you have a 3-meter span.
Yes, sensei.
So maybe 150, 100 to 75 elastic steel beam outside.
Okay. If it is too crowded for 3 elements here, we can do half viscoelastic and half metallic damper. Do you remember last time there's one research paper that have one stiffener and another one viscoelastic damper? So
yeah, it's possible you can delete this one.
Yes.
Yeah.
Okay.
Maybe the result doesn't change.
Okay, we can try that one, sensei. I will share you with this book in the Google Drive.
Oh yeah, it looks very
Yes.
nice.
Yes.
Is he professor at
I believe so, because It seems like the book that we purchased for this displacement design method is from the IUSS Press.
Could you go down? Any name of the university?
University Toronto.
Toronto. Toronto is
in Canada.
Canada. And University of Buffalo. It's a New York, United States. Okay. Okay. I want to read this book.
Hi. Okay. Yes. Thank you so much, Sensei. Oh, Sensei, sumimasen. I have another thing to show you about the Majima sent me to this. If we join the presentation at GES, after the presentation, I think we should submit for paper for review, because it said here the presentation is this is not considered as how can I say, review paper. So we have to send the our paper to the Japan Society Earthquake for review, and then it will consider as international conference.
I think this is a international conference. I don't know. Maybe.
And this is not a peer review paper. Yeah.
Yeah, of course I know.
Yeah. It's okay, Sensei. Yeah, of course. After you submit the abstract, and yeah, you should make after the symposium. You should submit again. Okay.
Yeah.
Okay, Sensei. Thank you so much.
And could you make an abstract?
Sensei, I used
You
to.
must submit before.
I already submitted the
May
apps.
18?
I already submitted the abstract. I already showed it to you last time.
Oh, really?
Yes.
But
yes. If you yes, it still can be edited. So don't worry. I will send the abstract again today to you. And then if you have comment, I will edit the abstract.
Okay. Who is next? Sarah-san, do you have something to show me?
Yes, I have. Okay. Now I'm gonna talk about capacity spectrum method. It's known CEC. And I pulled up 7th floor, and I added the walls of each size of this structure, and the weight is 5,000 kilonewton, and the height is 4 meters. And after the static pushover, it is indicated by this picture. Okay, and after that, story drift of each story is known as the it is the decision of fielding point depends on a level 2, and the highest from it from this high, we can calculate 2 centimeter in here.
So you assume 1/200 drift.
Yeah. And from this relationship of C SDX and SD, I get the value of SD when yielding is 8.457 centimeter in here. Oh, excuse me. Okay. And there in capacity curve, as indicated by this capacity curve, where the SD equal to 8.457 centimeter, I get the SA 150.3 go, and yeah, we call the point a yielding point with the optical ductility M1. And from this picture, the first one is relationship of natural period as known as T, and second graphic is a relationship of SD and AC. And the response spectrum depend is prepared in the case I follow Japanese way for exercise, and the response spectrum demand is still in between and SA and T. I use this formula to change the from T to SD. This first one is T and it is SD. Okay. And second, this is performance point, and in this point, the response spectrum demand is for the damping ratio high is 5% with the ductility factor M1. And from this, we can see an 8.457 and demand M2 double T and 16.914 and demand 3 demand spectrum M3, and we can see 25.371. And from this graphic, we can see performance point, and it is concluded spectrum capacity curve. And
so how do you obtain green spectrum and the blue spectrum?
Green and blue one?
Yeah, original spectrum is light blue, right? This one.
Light blue.
But you obtain green one and blue one. How did you get this?
It is did you see my Excel?
No.
Okay.
I can see only PDF file.
Okay. So see. Okay, did you see my screen? Okay. And demand is, first of all, demand spectrum 3 and spectrum.
This is 5% damping, right?
Yes. This is demand spectrum M3. This is M2. This is M1. And from this section, we can find the demand spectrum M1 and M2, M3.
What formula did you use?
Formula. This is actually.
What is 0.67? How did you get 0.67?
What? Can you repeat the second?
I can see 0.67 here, sir.
Oh, yes.
How did you get?
This is actually formula. I didn't.
Sarah-san, I think you missed one formula is the damping effective damping formula, HE. You forgot it, and then that's why we can get the 0.6 just now. You have to calculate.
Also, there is a reduction factor for
yes.
spectrum.
I can show you later, Sarah-san.
Okay.
Hi.
Okay. Okay, please continue.
Oh, okay. And after that, drop the performance point called by the connected red point dots, and in this point is the demand M1 and one, and this one is the demand M2. This one is demand 3. And the intersection of capacity curve with the performance point curve is called performance point. And after that, we can understand that the point is the response of building subject to the earthquake that has black star in here. In the response spectrum. And in this black star in here actually is 18 centimeter. From this 18 centimeter, we can see the story drift and shear force of each floor, and we can see in here 18.06 and shear force and the story drift we can see, yeah. And from this, drop this graphic, yeah.
Okay, that's all.
Yes, that's
okay. Very good. But you must, how to say, understand the formula. You didn't explain.
Okay.
There are some formula you must understand. Okay, please talk with Zafira-san.
Okay.
Okay, very good, very good.
Thank you. Can I stop?
Yeah.
Right.
Next is Ataya-san.
Yes, can you hear me?
Yeah. Okay.
Since I modified something in calculation of mass ratio, before I calculated mass ratio of each TMD, the mass of each TMD over total mass of the structure, but now I modified it. So equal mass distribution of total TMD mass for each of TMD. This is the mass of each TMD over total mass structure. So when mass distribution is done based on model mass, mass each TMD is divided to each model mass because I read it in a paper. Okay. And in this case, that mass distribution is done based on productive effective mass ratio and concentration factor. Then I divided mass of each TMD over my productive case to factor. So my result changed. And before that, also I used from the mode node text file of the output. Yes, the red line is for control and yellow line is for uncontrolled. You can see that the mode shape has changed, but the amplitude doesn't change as much as the location of TMD change. So it means that the location of TMD doesn't change in both cases, 7 story and 20 story. And also I calculated this mode shift of controlled and uncontrolled for three methods of mass distribution. In all cases, the location of TMD didn't change. But maybe for some cases it will change because we can see that mode shift has changed. And the second mode, I installed just only the first TMD and calculated and found that second mode shift. The right side is then I installed the first and second TMD and consider the first mode of control structure, that is the third mode of original structure. So in conclusion, we can say that in this case, the equation of TMD in case of control structure also the same.
Oh, okay.
And after modification, this was the result in theory throughout this graph. Horizontal displacement reduction in percentage, the vertical axis is in stories. So this is the reduction percentage by single TMC, the black line. Red line is the lambda mass distribution is based on the productive effective mass ratio and concentration factor. The green line is the mass distribution based on model mass, and the blue line is equal mass to each TMD. So we can see that on the central single TMD is better, but if we compare the method of mass distribution of multiple TMD, so the third method is better. In here, the third method is better ever than single TMD. In here, also better from all of them, just for 4 pairs stories that equal mass is better, but in other cases, the third method is better. In Sudoku, also we can see that the third method is much better. It means that they reduce the maximum displacement more than other methods.
Okay.
And this is the graph of the maximum displacement that you can see that except for in central and we get the red line is in the left side. It means that reduce much. In central case also, if we compare the multi TMD cases, the third method is better than other two methods, but only just a little larger than single TMD.
Okay.
And for 7 story also, we we can see that the red line, which is the third method, is better than other two methods, equal mass and mass distribution based on model mass. But in many cases, the multiple TMZ, when this mass distribution is done based on the third method, is somehow very close to single TMZ. But this two method is not good, especially on the shaft and the hook score. And on the center, it's also not more effective. Just in case of Kobe, they are somehow equal. It means equal mass distribution and the phase method is based on the effective mass distribution and participation factor. And this are the displacement graph that also you can see that the red line is in the west side. So overall, we can say that this method of mass distribution is very effective, maximum reduction, and
Okay, so you discussed only mass ratio, mass distribution.
yes, it's
So under thickness is related to the natural frequency of the building, right?
yes, there is a formula for frequency ratio, optimum frequency ratio, and also damping ratio.
Oh, okay.
And those formula is related to damping of structure and also mass ratio. So mass ratio is very important to calculate the frequency ratio and damping ratio.
Oh, okay.
So because of that, we can distribute the mass somehow effective. We can get effective mass ratio, and mass ratio is involved in the formula. And finally, we can find the damping coefficient and the stiffness, which is different in each case.
Oh, okay. So is this result consistent with the result of the second story? Same result? Same conclusion?
Yes, then here, this is for 20 story. The red line compared to other two institutes in 4 cases is better. Just in here and just 4 lower floors. But in all cases better than this 2 other methods.
Okay, so it is the same result.
Yes, and in here also since the red line is better than the blue line and green line in all cases. So we can say that this method of mass distribution is better than equal mass distribution and also mass distribution based on model mass.
Okay.
Because these two methods are done by some researchers already, and this is somehow a new method, and the logic is because the effective mass ratio and participation factor of each mode shape is very important and can influence or affect the total mass, the total responsive structure. Because in many research papers, researchers didn't concentrate to the amount of mass of each TMD, so maybe it's a good idea. And since I wrote an abstract, but I think it's wrong because I thought that here it says 300 words. I thought this 300 words is for English and 100 is for Japanese characters. So maybe it's wrong. Here it says maybe that 100 English words.
Yeah.
So I have to make it more summarized.
Only 100 words? So it is maybe 10 lines. one line, maybe 10 words.
Yes, there is, this is the Japanese statement that only translated in Google Translate, but is it 100 words in English?
Yeah. It is written 100 words in English.
So it has to be very,
Yeah.
because it is 230 words, so I have to reduce it to 100, and it will be very, very right.
Well, around 100, it's not so strict. Yeah, so maybe you can reduce the amount to maybe half.
There is not that maximum 100.
Well, this is approximately.
Okay. So I will make it half, around half.
Yeah.
And then I will send you for your comment.
Okay.
Thank you.
Yeah.
That's all.
Okay. サラヤさん、
Yes, Sensei.
I want to show you something. Okay. Screen. I made a hysteresis model for unbonding bearing.
Yes.
So if we run that program, okay. Something wrong. ちょっと待って、おかしいな。Anyway, I have a question. So this is a hysteresis.
Yes, sir.
I put number 1, 2, and 3 is here, and 4, 5,
Yes, sir.
6 is returned.
Yes.
And after boundary displacement, you said you stop the calculation.
Yes, sir.
But still cannot stop. We need some rule.
Okay.
Displacement is over boundary.
Okay, then.
So temporarily, I put another, slope from this point. And if you consider stopper, you can see very high stiffness, SB.
Yes.
If it's, I don't know, zero stiffness, it will be continue, same force.
Yes, sir.
So, and also, I just made this program last night, so
Okay.
it's compiling, so please wait.
Yes, sir. Sensei, the explanation that I had sent you, that was okay?
Yeah. Yeah. But I actually, なんていうのかな、well, I modified my bilinear hysteresis model
Yes, sir.
to match your.
Yes, yes, sir. Of course.
So when you option member isolator considered,
Yes,
and if you click isolator, and in the number 7 unbonding bearing,
okay, sir.
is it okay? How do you call it? Unbonded bearing or unbonding? Okay.
Uh,
I can fix it.
yes, sir. I think unbonded will be better.
Unbonded bearing. Okay, I will. Then if you put property,
Yes, sir.
so you input the first stiffness
Yes, sir.
and second stiffness ratio,
Yes,
third stiffness ratio, it will be almost zero.
yes,
And first value is 1,
yes,
and the second value is 2.
yes,
And boundary displacement,
yes,
so this is a parameter you should input.
yes, sir. This is perfectly okay. Yeah.
I will check if it works. And, I don't know. So, so it will be 1 centimeter yielding, and the boundary, I don't know, 500. The first time it doesn't work. Small prototype. And, only one element. I restrict the horizontal direction only.
Yes,
2, 3, 4, 5, 6, 7. Yeah. Something wrong. Okay, it doesn't work. I will try to finish this.
yes, sir. No problem.
So it's almost well completed. I hope.
Yes, sir.
So maybe this weekend I can.
Yes, sir.
And Saraya-san, do you have anything you want to discuss?
Yes, sir. Yes, I can. Can I share my screen?
Yeah.
Yes. Is my screen visible?
Yeah, I can see. Yeah.
Yes. Since the last time we had the meeting where we were discussing my building was not analysis was not correctly completing at first. So I used the same natural rubber bearing
Okay.
with this stiffness as discussed earlier. And now if we unrestrict the second direction as we already saw in the last meeting, then it is working. The analysis is getting complete. And I don't know why, but if we restrict the second direction also, it is not working, the program. So, anyways, I unrestricted the 1 and 2 directions.
Okay.
And what I did, I used the damping factor of 18% because that was the damping factor of the isolation system. And since the whole building is rigid, so I considered 18% for whole damping. And
maybe it doesn't work.
Yes, like small differences coming with my program actually. Then I input the earthquake load, and this kind of difference is coming with my MATLAB and the Stera results. So still it is like matching to some extent. So in the MATLAB, the acceleration, the higher mode contribution are more like there is more acceleration in higher modes also. But in Stera, it is pretty smooth. Then I checked for the wind response also. So wind response also it is coming quite good. However, I'll have to also check the accuracy because in wind the time steps are quite large. So if we reduce them, we can get more accurate results. And then Sensei, as we discussed, I also tried with the lead rubber bearing. And with the lead rubber bearing, I used these parameters. So these parameters actually concluded to 2 seconds time period. So I just use random parameters to get 2 seconds time period, and I use the same parameters for my MATLAB program also. And then I compared the results to validate. So and now again, what I saw is for earthquake, it is matching very nicely, like almost matching. And for wind, it is not matching, but the reason is since it is taking a lot of time. So earlier I was showing you the results of my wind data in my first meeting. So when I was saying that the wind response is very high as compared to the uncontrolled response. So then I reduced the time step, and I actually got a wind response that is less than even half of that. Because it is highly nonlinear, because the trilinear model which I have prepared, it requires more small time steps. So, but this program in MATLAB is taking 8 hours to give me the results. So, yes, Sensei. So in Stera also I'll try with more finer time steps. Stera is more or less like more easily converging, because I think in Stera we use the implicit integration method. In MATLAB it is explicit method, the Rangagutta method, so it is taking more time actually. And however, there is some mismatch with the Stera and MATLAB. I think it could be gone with like more, because for earthquake it is matching perfectly fine. So I think if the time history is same, it will be the same result.
I don't think so. I don't think so, because you assume bilinear. In case of wind, because wind is very small, first stiffness affect the result much in case of bilinear.
Yes.
So I think your result is responsible. You should check the hysteresis of the isolation layer.
Oh, yes.
Yeah, I believe wind must consider the hysteresis. Response may be different. But earthquake, I'm also interested in the hysteresis of the earthquake response. Yeah.
Yes.
If large
I,
maybe I think this case isolation layer for area, right?
yes. Yes.
And probably hysteresis looks like a similar to bias
Yes. Yes.
in both cases.
Mm.
But the wind, in case of wind, uh, I mean, fast slope is quite different between Vela and Matsuda. Yeah, you should
Yes.
this hysteresis of isolation layer.
Yes. Yes. I'll check that. So the comparisons which I did between to validate my Stera model, and then since I also included the actual reinforcement details. Earlier, I only included the shapes of columns and beams. So now I also included the reinforcement, and I considered nonlinear shear string and nonlinear flexural string. And then I checked the time period of the structure, uncontrolled structure. So it is some 3.393. Earlier it was somewhere around 3.7. So it has increased slightly.
Oh,
And,
yeah, but
yes, yes.
that's okay.
Yes, very solid. And since then I did the nonlinear static analysis, and I am getting this kind of result for 1/50 drift ratio.
Which one is the isolation layer?
Here, since this is uncontrolled, this is not base isolated.
But it looks yielding happen in the middle of column.
Yes, sensei.
Why such a strange yielding?
I don't know. I like to check.
Maybe shear reinforcement is so small.
Okay, sensei. Uh, Actually, sensei, shear reinforcement. Okay. Actually, means in the actual drawings, some of the reinforcement were different than it was available in Stera. So I tried to calculate the equivalent steel ratio and give some reinforcement. So maybe for shear it is less. I will correct that.
Yeah. So if there is a column, if
Yes,
fracture yielding, you will observe hinge, I mean yellow mark, bottom and top.
Okay.
But if element yielding by shear, you will observe yellow mark in the middle.
Oh, okay.
So I noticed you observe middle. I mean shear failure in second story and maybe first story also.
Yes, sir. The first one. Yes,
So please check.
yes, sir. I'll check. And since after that, now I will have to also install the TMD to the base isolated building. So I am trying to model that. Currently, I have not finished this modeling. What I am trying to do is I have added one more story after the first story, and then I have in one level I have only the TMD, and then I have divided the columns into two by dividing the height of the columns, and I will have to execute this to see whether my results are matching.
Yeah, but please be careful. So this, I mean, if you have a slab, you can assume rigid.
Yes, sir.
If you have a slab, you can assume rigid. But on the top of one layer in the middle,
Yes, sir.
there's no slab, right?
Yes, sir.
So in this case, you must select the flexible floor.
Okay.
So from option member,
Yes, sir.
you should select mixed
Oh,
floor,
yes.
and you can select I mean TMD layer to be flexible.
Okay. 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 Okay, since I'll check that and I. And one more thing is
Yeah.
the date of the abstract submission for the World Conference is 15th, which is Monday. And right now means I am still working on the Stera model. So I don't know how I will write the abstract. I will try to write, and maybe by the weekend I can write something for the abstract.
Okay.
I don't know. Maybe the date will extend, but I am not sure.
Okay.
So maybe by the weekend I can send you the one abstract.
Yeah. Okay. Any other people who want to discuss? 真島君、なんかある？いいですか？はいはい。
予測実験。
はいはいはいはい。
ワープ見えますか？
はい。
実験の結果だけしか今日持ってきてないんですけど、A の変異は、変異の遅刻的波形で、青色が振動剤の入力変異、赤色がワイヤーの行動変異で、増幅しているので、だいたい10倍ぐらいになっていて、この増幅した変異とダンパーの履歴を書くと C のような、結構綺麗な形になってます。これが入力が 0.1Hz の時で、0.5Hz を入れても、形は大体同じです。
横軸の速度って結構大きいね。1000とか100回ってこと？だから150回ぐらい。
はい、そうです。はい。50回。
結構大きいね。はいはいはい。
で、これが実験の 0.5Hz の時の結果で、前回特区からもらった試験結果を元に予測していた結果があって、もう点数は比例するだろうって考えると、このオレンジ色の線が TD5800 の3000の時の予測の結果で、これだとちょっと速度が足りないので、近似曲線を黒色で描いて、やってみると1500でだいたい26ニュートンぐらいっていうのが予測の結果で、これを実験の結果と比べると、さっきの 0.5Hz の時1600ミリ、メーターパーセカンドの時62ニュートンだったので、これが両方2個ついてるので、かける2倍すると、大きくは外れてないかなっていう。
もう一回一つ前のスライド言って。
これは
6.3。
はい、1個あたりの予測の結果が 26.3 ニュートンで、ダンパーは両端に2つついてるので、これかける2倍すると52ニュートンぐらいになるので、
そっか、今回62だから、
はい、そこまで離れてるわけでは
そうだね。よかったよかった。
で、この時の速度が1600なんですけど、透過速度で考えてみても、最大振幅500ミリで、2π×0.5Hz で1570になったので、結果も悪く、この速度の結果も悪くないなっていう感じです。
はいはい。
これが3000のタイプで、あと5000と8000があるんですけど、それはまだ実験してなくて、で、音が出る原因がやっと分かって、その後ろにあるタワーのところで重りが上下に動いてるんですけど、そこの後ろに重りが大きく触れないようにガイドワイヤーをつけていて、このガイドワイヤーに沿って動くときに音が響いてるみたいで、もうどうしようもできないので、これはもう通常に実験しても音が鳴っちゃうので、次の実験は土曜日にやる予定です。
なんか下の階のね、方の入って文句言ってるのが、
中野先生ですよね。
そう。
はい。
中野先生には、言っといたら土曜日実験しますとか、どの日に中野先生がいるかどうかわかんないじゃない。もしかしたら土曜日にいるかもよ。
自分の人から土日はもう自由にしていいって言われたんですけど。
いや、自由にしても中野先生がいなければ、いつやったっていいんだよ。逆にいるときは、 土日だろうが、やっぱ迷惑がかかるんで、
5月23だけはやめてって言われました。他の日はまあいい。
だから一応中野先生に、まあ、言った方がいいんじゃない？土曜日だから大丈夫だと思いましたって言ったって中野先生がなんか言われたら、ね、
まあ、それは
ないじゃん。中野先生のメールアドレスとかわかる？
いや、後でホームページで調べてみます。
まあ、一言お詫びして、先生の、まあ、土曜日だったら先生、にやろうと思いますが、先生もし、その時、いるようでしたらまた、違う日を考えますとかさ。あるいは、どの日だと先生、例えば授業でいない日とかね、はい、実験してもいい時間帯をちょっとご相談したいのでって言って、一日の間でこの時間帯は大丈夫とか教えていただければ、その時間に合わせますとかさ、はい、まあ、その方が人間関係がうまくいくように。
わかりました。
騒音問題って、あれだからな、結構、事件が起きるからね。マンションとかね。気をつけよう。でも結果はすごく良かったね。
はい。0.5Hz 以上になると、なんか、振動台の方の音がおかしくて、ちょっと、今はやってないです。怖くて。で、多分響いてる原因が、このタワーの下、直接アンカーボルト打ってるんですけど、多分これで、この下になんか鉄骨みたいなのが入ってるみたいで、多分それ伝って、
そうだね。
響いちゃってるん
ですね。なんともしようがないな、すぐにはな。
この実験はもう、どうしようもできないです。
まあ、中野先生にはさ、あと何回ぐらいで、多分終わると思いますとかも言っとけば、はい、まあ、ね、ずっと続くんだったら、あれだけど、そんな程度かとかさ、思ってくれると助かるね。
で、あと、去年の全体ゼミであった日本工学会のシンポジウムなんですけど、これって4年に1回なんですか？
あれ、そうそうそう。
なんか意外と大きいやつだな。
世界地震工学会議の、はい、まあ、4年に1回なので、それと重ならない年にやるんだよ。
なんか意外と大きかったので、行ってみようかなって思って、内容としてはなんか校外相当で査読論文と重なっては問題ありませんって書いてあったんで、動画視点除システムの1方向過信実験と解析結果と2方向の実験と解析結果を一つにまとめて、これはまだどこにも発表しないんで、まとめたものは。で、あと、ダンパーとか摩擦のエネルギー吸収量と、導火原子がどう推移していくかぐらいをまとめて、出そうかなって考えたんですけど、どうですかね。
いいんじゃない？出した方がいいんじゃない？
わかりました。はい。じゃあ、後で公開書いて送ります。
はい。
以上です。
はい。OK. So, shall we discuss next meeting? 11. で、来週は、I'm absent next week. So, next week, very busy. どうしようかな。Okay, so, 29, 30, 31, 30か31の午前中、morning in 30 or 31, I'm okay. Or 1st of June, morning, 10 o'clock. which one you prefer? 10 o'clock, 30, or 31, or 1st of June?
31 is okay.
Any time is okay?
Yeah.
So, shall we make it 30?
Okay です。
30 and 10 o'clock in the morning. Okay. Okay. So, shall we stop? See you.
はい。ありがとうございます。